Okay. So we're going to start with electrical principles. So today, basically, the majority of the math type questions that you're going to get, there's a few later on dealing with wavelength and some things like that, but this is the majority of it. We're going to start off with resonance and Q. Resonant circuits is kind of the main principle in radio. If you didn't have resonant circuits, you'd have a hard time generating an electromagnetic wave. The next group, we'll talk about time constants and phase relationships. Then we get into coordinate systems, rectangular and polar. Some of the newer stuff they've added is in the RF effects and components and circuits. So we talk more about skin effect and parasitics and inductance, capacitance in components. And then the other question, electrical length of conductors, and I'll mention that when we get there. I can't explain it. I researched it. I know the answer. I can prove the answer. I can't tell you why. I thought Roman Schick's book would. He punted. He said, this is the answer. There it is. The ARL book, the same thing. Here's the question. That's the answer. So fortunately, there's just that one question, and you'll remember that answer. Okay, so we'll talk about resonance, serial and parallel, the effects of Q and the half power bandwidth. As you all should remember, resonance is defined in a RLC circuit when the inductive and capacitive reactances are equal. So they essentially cancel out, and it looks like a purely resistive circuit at the resonant frequency. The formula for inductive reactance, which you should remember, is 2 pi times the frequency times the inductance. When I learned it in college, we used omega L, and omega is equal to 2 pi F. It's just a lot easier to write omega than it is 2 pi F. Capacitive reactance is the reciprocal of 2 pi times the frequency times the capacitance. And if you remember from the basic stuff, the inductance is really a measure of the amount of energy stored, and the capacitance is the amount of energy stored. In one case, it's in a magnetic field. The other case, it's an electrostatic field. So if you work out and you set the two reactances equal, you can solve it for the resonant frequency, which is what I showed there, which is 1 over 2 pi times the square root of the product, the inductance and capacitance. Now, there are several questions on that you'll probably have to work with your calculator, because they're going to give you microfarads or picofarads and microhenries. If you're good at approximating, you might be able to do it in your head without a calculator. But I would practice doing those kind with your calculator. This is a series RLC circuit that I set up. I use a little simulator called Circuit Lab, which lets you put together circuits and then run time and frequency domain analysis on it. So we just have a 50 ohm resistance in series with a 1 nanofarad capacitor and a 1 millihenry inductor. And if we look at that over the frequency spectrum, you can see that the reactance or the impedance for that capacitor She got this one right. Right. Down here at, I can't quite make it out. It's very low frequency, close to 0 hertz. It's got a very high reactance. As the frequency goes up, you see that it drops down. If it was a perfect capacitor, it would drop to 0. And if it was a perfect capacitor, it would be an infinite reactance at 0 frequency. The blue line is the inductor, which is just the opposite. It's going to appear as 0 resistance or reactance at 0 frequency and increase as it goes up. You see where the two cross, they're equal, and that's going to be the resonant frequency, which is plotted down below. So you see for a series resonant circuit, it's going to appear at as a very high impedance at a low frequency and a very high impedance at a high frequency, but it's going to appear as essentially 0 at the resonant frequency. The other thing that we'll talk about a little bit later, as you approach the resonant frequency, the phase is going to change. You're going to start off with a 90-degree phase shift until you get very close to the resonant frequency. You're going to have 0 phase shift at the resonant frequency, and then it's going to start becoming a minus 90-degree phase shift because it becomes capacitive. If you look at the parallel resonant circuit, what you'll see is, again, the capacitor is going to be high and go low with a higher frequency. The inductor is just the opposite, where they're both equal. It is your resonant point. The difference is, in the parallel, it's going to appear as a 0 resistance or impedance at low frequency and at high frequency. And it's going to appear as an infinite at the resonant frequency. So that's really the difference. In series, it starts off high and goes to 0. In parallel, it starts off low and goes high. So an example of how you calculate this, if you got a circuit and you got 50 ohms in series, it really doesn't matter if it's series or parallel for this one. 40 microhenry inductor and a 50 picofarad capacitor. So if you plug those into the formula and do it in 10 to the minus 6 to minus 12 powers, some people can do that in their head. If you're using the calculator, it's fairly easy. You really need, most calculators, you need to work from the inside out. And you can't have too many parentheses. That's where you can get in trouble with the calculator because of the precedence of multiplication and addition and division. So, is everybody clear on that example?
Bob, I have one question.
Okay.
Would it be easiest to work the 40 times 10 to the 6th or minus 6 times 50 by times 10 to the 12th by subtracting or dividing these two? So it would really be 40 times 50.
That's 10 to the minus 18.
Okay, so it
when
would
you
have
multiply,
to be.
when you multiply, you add the exponents.
Got it.
So it would be
Thank
40
you.
times 50 or 2,000 times 10 to the minus 18th. So
Okay,
the minus 18th, easy, because the square root of that is going to be a minus 9. But I don't know the square root of 2,000 off the top of my head.
Gotcha.
So let's do a real question. We got a 22 ohm resistor, a 50 microhenry inductor, and a 40 picofarad capacitor. What is the resonant frequency?
It's a memorization question.
No, it's not. Now, the other thing I can't guarantee, but the order of the answers on a real exam may be different than they are in the question pool.
Mhm.
So if you try to just remember it's B or C, that'll mess you up.
Is that the 2 pi FL formula?
1/2 pi times the square root of LC.
Hmm.
So it's going to be 40 times 50.
Mhm.
Add the exponents. Kind of sounds familiar. Like maybe it's the minus 18 again.
So here's the trick. If you're doing this and you have multiple choice, just put 40 times 50, take the square root of that. Instead of worrying about where the decimals are.
Mhm.
And when your answer comes out, it's gonna look like one of those answers,
Mhm.
the zero.
Now, the other thing, in almost all of these multiple choices, well, they're all multiple choice, you're going to have two answers that are way out in left field. So you're kind of down to two possible. And even if you approximate, you're going to be closer to one than the other.
Mhm.
Anybody got an answer?
See, so like I was saying, if you take the 50 times 40, take the square root of that, times 2 pi, take the inverse of it, and it'll come out to like 0.00035557, whatever. And that'll give you your answer. Does that make sense? I always look for the shortcuts, so.
Well, that's good. Calculators can mess you up. I can verify it. Ready for the answer?
Mhm.
I mean, 1/6.28 times the square root of that, which I don't remember off the top of my head. Okay.
Oh, please hold on.
And there's just a plot of that circuit we just did, and it's 3.56 megahertz according to the simulator. Okay, what's the resonant frequency of another circuit? 33 ohm resistor, 50 microhenry inductor, and 10 picofarad capacitor. Same problem, just slightly different numbers. Plus they threw in megahertz and kilohertz in the answer. Anybody got an answer?
Not a correct one.
Well, yeah, you don't know.
Hmm?
You don't know unless you're not coming up with anything close.
Oh, my God.
I think one of these is the one I missed on my exam.
Hmm.
Because I had a different calculator and I couldn't come up with anything close. And I guessed. I never guessed right.
That would be my strategy. Finance.
Well, I was told by one of our examinees one time, an old Navy guy, who said he used to ace all of the tests. And in the exam room, he would look at, for each question, he would look at the clock. Because they were all multiple choice for. And depending on what quarter the second hand was the answer. And he claimed it worked.
Or if you look at a lot of them, there's another method, it's called too long to be wrong. And if you, most of the questions in there, if they have an explanation, it's the long explanation, so right. Almost every single one.
All right, well, let's see what it is here. 7.12,
That's what I guessed.
twice as much as the other one.
Mhm.
Because this was 50 times 10 to the minus 18. The other one was 2,000. So the difference is a quarter. Right? And the square root of a quarter is a half. So 1 over a half is times 2.
Okay.
Anybody follow that? That's okay. Try to use your calculator. Or remember the answer, which is younger people can do that. It's much harder if you get my age.
I can't figure out where my math is coming out wrong. That's what I'm trying to figure out.
Well, I had the same problem.
You're putting the formula.
And then I got nervous and I kept making more.
Right.
I gave up. Okay, so when we have a series RLC circuit, we know that at resonance, the reactances are equal, so we're only left with the resisting part of the circuit. So if there's a series resistor in a series RLC circuit, then the impedance of that circuit at resonance is going to be basically equal to the real resistance values. In the parallel circuit, it turns out because they're in parallel, even though the impedance of the capacitor inductor is going to be essentially infinite, it's in parallel with the resistor of a fixed value. So it's going to be equal to or slightly less than the R value. So in either case, at resonance, the parallel or the series circuit is effectively going to be equal to the series or parallel resistance in the circuit. Does everybody know how to do parallel resistors? Or parallel inductors or series capacitors? The reciprocal of the sum of the reciprocal formula?
I used to.
We'll get to that one. I don't know if that was on the general or not. I think it is. And this is just another plot showing how the series circuit works versus the parallel. So they're just essentially reciprocal of one another.
Resistance is just thrown in there to throw you off.
In those questions, yes, it's not. If you notice, there's no R in that formula for resonant frequency. But if you were to calculate the impedance, then R is in there because it's it's R plus J X. So it's a vector. And the X is actually the phase shifted reactance. It's either going to be 90 degrees or minus 90 degrees, depending whether it's inductive or capacitive. So another real question, what's the magnitude of the impedance of a series RLC circuit at resonance? Remember, series circuit, because you've got a capacitor and inductor, the capacitor looks like an open circuit at 0, right? And the inductor looks like an open circuit at very high frequency. So at those extremes, it's going to look like an open circuit. When it's at resonance, it's going to go to 0 or whatever the R value is. Any guesses?
D.
I hear a delta. How about that? Everybody get that one?
Let's see.
Okay, remember, impedance is this vector of the real resistance plus the reactance. And we use the symbol J to represent the square root of -1, which is really representing a phase shifted value. It's 90 degrees orthogonal to the real. And when you plot it, which we'll get to in a little bit, that's why you do that on the y-axis.
So actually, that would be the same question if it was parallel as well.
Yes,
Okay.
the answer is going to be the same. That might be the next question.
Oh.
So what do you think the answer to this one is?
Would be A. Oh, I'm sorry, wait a minute.
Yeah,
Circuit
now
versus inductive,
the other thing,
so B.
carefully read the question. Read all 4 answers before you answer. A lot of times you'll quickly read the question, you think you're familiar with it, but it might be one word different, and you might find an answer that sounds right before you get to the correct one.
Good point.
There's no rush, there's no time limit on the exam. So, alpha. Okay, kind of talk about all this stuff. When you're actually at resonance in the parallel LC circuit, we kind of tend to call those tank circuits. The input current, because it looks like it's a high impedance, is going to be very low. That's going to be whatever the resistive value is. You can have circulating currents because of the energy in the magnetic field is increasing and then it decreases and that energy gets transferred over to the capacitor for an electrostatic field and it just goes back and forth. And if they were perfect inductors and capacitors, it would oscillate forever, but because there's losses, it doesn't, so you have to keep feeding it a little energy to keep it going. But the circulating currents can be extremely high in that case, even though from the outside, it's going to be whatever the voltage divided by R is. So what is the magnitude of the current at the input of a parallel RLC circuit at resonance?
It's R//S/R.
Resistance divided by inductance or inductance divided by resistance? I'll give you a clue. Those are the left fielders.
Yeah, I was looking parallel, and so parallel is minimum.
Bob?
Very good. Question?
Bob? Yes,
Yeah.
well, just a point. My my antenna analyzer, the Comet antenna analyzer, when it's an open circuit, both needles are parallel. And when it is at resonance, both needles cross. So maybe that's a good way of remembering open and resonant circles. So, both of them are at minimum for that particular resonance. Does that sound good? Yeah.
Yeah.
So it kind
Except
of,
in your- Go ahead.
it's kind of a mind picture as opposed to the actual calculation in your head. Maybe that's helpful. I don't know.
Okay. Let's see what we got next. What is the magnitude of the circulating current within the components of a parallel LC circuit at resonance?
Well, my guess would be that it's not, well, I don't know. I can't say. See, now that's an example where it would not help.
Any guesses? Alpha, Baker, Charlie, Delta.
B.
Because as somebody said, those long answers tend to be wrong. It's maximum. So the current within that loop can get extremely high. We're going to talk about series, and of course it works the opposite. You can, because of the circulating currents, you can get some very high voltages, thousands of volts actually, even though you might only have a few volts into the circuit, depending on the Q, which we haven't got to, of the circuit itself. So the higher the Q, the more it looks like perfect inductors and capacitors, the higher those voltages can be. What can cause the voltage across reactances in a series RLC circuit to be higher than the voltage applied to the entire circuit? This is an easy one. That's what we're talking about.
Resonance.
I mean, it's not resistance.
Right.
Or capacity.
And we hadn't talked about conductance yet.
Okay, so it would be resonance. Okay,
Yep. It's not the capacitance, it's the fact that it's at resonant frequency.
right.
And like I mentioned before, you can see the phase shift as you approach resonance. So you've got a 90-degree phase shift, which means it looks inductive. At resonance, you go to zero phase. So it's purely resistive. There's no phase component, so there's no reactive component. And then you start going minus 90-degree phase shift.
Okay,
This thing's always in the way. What is the phase relationship between the current through and the voltage across a series resonant circuit at resonance? What happens at resonance?
You're in the middle of the. Big peak is on there.
mhm. I mean, I have a guess, but
What's this is plus 90, this is minus 90, this is 0. Phase.
Yeah, the only thing that's what I was gonna pick, but the thing I wondered about is when you're talking about the voltage increasing. But that just means they're in phase. Because the
Right.
current and the voltage are in phase, okay,
Well, at resonance, they're both in phase, so
right,
you're
even though it can be more. Okay,
correct. That's just due to the circulating currents and the amount of. Okay. Q, I mentioned Q, which is called quality factor. And it's a measure of how closely a component or a circuit behaves compared to the ideal, the theoretical. So, you know, a Q of infinity means they're perfect inductors and capacitors, but that's not the real world. There's several kind of definitions of Q. One is it's the ratio of the energy stored divided by the energy dissipated. So obviously, if you had no resistance in the circuit, you're not going to dissipate any power. So Q is going to be the energy stored divided by 0 or infinite. Since the reactances are equal at resonance, if you have a parallel resonant circuit, the Q is going to be the resistance divided by the effective reactance, whether it's inductive or capacity. If you have a series circuit, it's going to be the reactance divided by the resistance. I always have trouble remembering that one
okay,
because I can't quite wrap around my head on exactly why that's the case, but
what was that difference again? The series?
parallel is resistance divided by reactance. Series is reactance divided by resistance.
Now, I just have a question that every student that enters algebra always asks. Where is this used? Like, what are you using? When are you pulling these formulas out and using them?
In the test.
Oh, for the exam? No, actually, if you're not into building or
Yeah.
designing circuits, radio stuff, testing it, repairing it, you probably won't use it,
Okay,
but it's on the exam
exactly right.
because the exam is to cover people that are doing, you know, any phase of amateur radio. There's some people that only, you know, talk on a handy talk. There's some people, all they do is contest. There's other people that build stuff.
Mhm.
There's people that experiment with weird stuff.
Okay, well,
It's got to cover.
yeah,
Yeah, so the thing is, like, if you decide you want to start making your own antennas or building your own antenna tuners or
Right.
something, like that's the beauty about amateur radio is there's 1,000 different places where you can get involved. You could just get a microphone and buy stuff off the, out of amateur radio out there, but if you wanted to take the next step,
Yeah.
push yourself and design something and implement something, that this is the kind of stuff that I think would be
very helpful, yeah, okay.
And if nothing else, I always look at it license as an amateur radio breeder, or even the pilot's license. It's just a license to learn more.
Mhm.
So all they've done now is giving you the basics.
Right,
Now to go out and make magic. Right?
right.
You know, you have to learn this stuff in electrical engineering.
Mhm.
I hardly used it after I went to work at NASA because it was mostly digital circuits and stuff, computers. How is the Q of an RLC parallel resonant circuit calculated? Parallel circuit.
It's harmless,
You just have to remember which formula.
right?
See. Mm-hmm.
Did you say delta?
Charlie.
Charlie. Yeah, try using the phonetic alphabet. I understand it better.
I second the Charlie.
Two Charlies, okay. I see another Charlie back there. Looks like Charlie's the winner. So resistance divided by the reactance. The effective reactance, because if you had both inductive and capacity, okay, you've got to subtract the capacity from the inductive, and whichever one is the result, whether it's positive or negative, which would affect the phase, but the Q is still going to be the same. Okay. Like I said before, the higher the Q, the more it behaves like an ideal circuit. Basically, the narrower the bandwidth that it'll be resonant at. And the higher the internal voltages and currents can be. So they can get extremely high, the higher the Q of the circuit is, because you have very little dissipative resistance, which is another thing. If you're somebody actually building equipment, okay, you'd have to take into account the fact that those resistors and basically the capacitors that you're using are going to have to be rated for several thousand volts as opposed to just your normal 50-volt capacitor. Even if we're looking at doing an in-fed half-wave antenna build, and most of the designs use a little 100 picofarad capacitor on that. And even doing it on a QRP radio, it still needs to be a very high voltage capacitor, because you can get some very high voltages on the end of that antenna. What's an effect of increasing Q in a series resonant circuit?
Read the answer. I said Charlie.
You say Charlie. I see a Charlie. Amy?
That's what I was considering. You can read through those and you're like, no.
What can you eliminate?
So
Phase shift is not. Okay. We haven't even talked about parasitic effects yet.
So if it was, you had a Q, an ideal circuit, you would have acidic resonance or inductance, right?
Mhm.
So and then the phase shift becomes uncontrolled. I'm not sure that.
And fewer components needed. Where'd that come from?
Yeah.
Right.
So the internal voltages increase. The higher the Q, the higher those voltages will be. Okay. Half power bandwidth. It's also a function of Q. So for a series circuit resonant, it's defined as the bandwidth that will pass half of the power of the input signal. So in other words, you're going to have a signal coming into that circuit, and at a lower frequency, it's only going to pass a small portion of it. As you get closer to the resonant frequency, the power that's going through it will get up to 0.707 or half power. And then on the higher end, you got the same thing as it's decreasing. It'll be 0.707. So the frequency range between the upper and lower half power points is called the half power bandwidth. And that's defined as the frequency divided by the Q. So it's the same, basically the same effect on a series and a resonant. In one case, you're passing a signal, in the other case, you're blocking a signal. Any questions on that one? Because we have a question coming.
No, okay.
What is the half power bandwidth of a resonant circuit? It has a resonant frequency. There's that old 7.1 that we just had, and a Q of 150. So if I just did a quick approximation. If I divided 7.1 by 100, that's going to be what, 71 kilohertz. So if I divide it by 150, it's going to be less than 71 kilohertz. So
Really?
you think it's Charlie? Got some nods. Charlie. It's a simple divide by. It's just you got to keep track of the decimal point. What's the half power bandwidth of a resonant circuit? It has a resonant frequency of 3.7 megahertz and a Q of 118.
Much like our friend Charlie.
Mm-hmm.
A lot of Charlies. Charlie's popular. Okay. You can use these resonant circuits for impedance matching. So if you need to match your antenna to your transmitter, you can use a resonant circuit in there to do that match where you can get or reduce your standing wave ratio and get the impedance of your transmitter, which is normally going to be 50 ohms, to better match the antenna, which may be anywhere from as low as 20 or so up to several hundred, depending on the antenna configuration. And because we just learned that the half power bandwidth is the frequency divided by the Q of the components of the circuit, as you increase the Q, the bandwidth decreases. In other words, the half power bandwidth narrows. And as you decrease the Q, obviously it gets wider. If you had a Q of 1, then basically it's going to be a flat across the spectrum. If you had a Q of several thousand, it's going to be very, very narrow. So the Q of the components will affect when you're doing a matching network, what kind of bandwidth you can do the match over. Obviously, when you have a lower Q circuit, you're going to have more loss too. So you're not going to get all the power through it either. What's the result of increasing the Q of an impedance matching circuit?
A.
Okay, so we learned about capacitive inductive reactance, resonant frequencies. What affects series and parallel circuits have on the behavior, whether it's high impedance or low impedance at resonance. And the Q, which are the ones that I could never, really had a hard time remembering these. So